Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullah. In the last video, we were at high-pass filter design and we learned how to design the high-pass filter. We will move on now into the band-pass filter design. But a quick overview that what we have learned is that the high-pass filter specifications are given and cutoff frequency has been instructed. Insertion loss at what frequency is given and what insertion loss, and then from there we get 0.5 with the help of this equation, and with the 15 dB insertion loss and this one we find the order. We got the order of 5, so we find out the elements values, not this one, this 5, and then we have designed a low pass prototype first, and then we converted according to this chart. If there is inductor, it becomes capacitor. So, and the capacitor become inductor. So here the capacitor become inductor, and the inductor become capacitor, and so on and so forth. And we use this equation, not the equation. This equation is different than the equation we use for low pass filter. This is 8.7, 0A and B. We use this one for the to find out these values. So it's just simple as that. So we will move on to bandpass filter, which is a little bit. It's not so difficult, but it's like steps are a little bit more than high pass and low pass. As usual, here it's given that we have to design a 0.5 dB equal ripple bandpass filter. So remember this one. This is 0.5 dB equal ripple. So we cannot use the maximally flat that we have used before these two designs in the high pass and low pass. And also we cannot use it for 3 dB equal ripple also. So we need to find out which one is belong to 0.5 dB equal ripple chart, and then from that chart and then from specific that table we need to find out our concerning values. But these band pass and band reject filter approximations are a little different than the low pass and high pass, as we know that there are two different cutoff frequencies and one center frequency involvement here. So that is what makes it a little different than the other two filter approximation. So now let's see what actually given here. So design a 0.5 dB equal ripple band pass filter. So we know a band pass filter which is 0.5 dB, ripples 0.5 dB with a center frequency 3.8. So our center frequency is given. So 3.8 gigahertz is center frequency is given, and the insertion loss at 11 gigahertz, given that the insertion loss is 50 dB somewhere. This is somewhere here, very far distance. So we need to see. So we find our f here. We're going to use here this value f, and we're gonna use our one more thing is bandwidth. So we have the our center frequency, we have our insertion loss point of frequency, and we have our ripple. But how are we going to find out our cutoff frequency 1, the lower cutoff frequency, and cutoff frequency 2? Since we can see that for a bandwidth of 100 megahertz means the bandwidth is given. Since the bandwidth is given, we know that the bandwidth starts from the cutoff frequency 1 and ends with the cutoff frequency 2. So F2 minus F1 is the band actually. So it means that the center frequency, at the center frequency, this is half of the bandwidth and this is half of the bandwidth. So as with the center frequency, if we subtract half of the bandwidth, we'll get this one. And from the center frequency, if we add half of the bandwidth, which is 50 megahertz, we add here, we'll get the F2. So now the lower cutoff frequency is 3.8 gigahertz minus 100 megahertz divided by 2, which is this one is 50 megahertz. So we find out 3.75 gigahertz. So this is 3.75 gigahertz. Similarly, we find out that this point is 3.85 gigahertz. So from there, actually, we find out our cutoff frequency 1 and cutoff frequency 2. However, to find out the center frequency, if this is not given, if only the upper and lower cutoff frequency is given, then we need to find out what is our center frequency. Our center frequency can be found out from this. So center frequency is equal to root over of F1 multiplied by F2. So if we multiply with this 2 and then we make a root over square root of this multiplication, we get exactly 3.8 gigahertz. But however, we usually we use omega on this one. So don't worry about this. If there is omega here, like omega naught is equal to square root of omega 1 and omega 2, it's as simple as that. It's the same. So at the end, it will give you the gigahertz also. So we find out our necessary things: center frequency, insertion loss and insertion loss frequencies, what ripple we have, the bandwidth. From the bandwidth, we find out what is our cutoff frequencies and what is our center frequency. We know, but we will verify with this one. But there is one more term which is very important, because since it have a limited bandwidth, not like unlimited like the high pass and low pass, it have a limited bandwidth. So we need to scale it for the bandwidth also. So we need to know what is the fractional bandwidth, the ratio between the center frequency and the bandwidth. So this is the bandwidth. So W, actually this will be reverse. This will be W2 minus W1. It's supposed to be W2 minus W1. Sorry, this is my mistake, but you correct them when you do the calculation. So it's supposed to be W2 minus W1 divided by the center frequency. So this is what we call the fractional bandwidth. So the fractional bandwidth value is 0.0263. So we keep it in mind. Later on in the equations, we need to use these values to scale our impedance and the inductance and capacitance values. So in similar fashion, we're gonna do the order checking, that what order we have. So we're gonna use this this frequency here, twice pi of this frequency, and then twice pi f naught of this frequency here, to find out that this is 2. So if this is 2 and we have 50 dB, so from 0.5 dB equal ripple, we need to find out what is our order. So here we find out at 50 dB we make a line, and then at 2 we make another line, and then this point we find out that this is higher than 4. So it means that our order should be taken higher of the 4, means 5. So the our element of or order of our filter is 5. So n is equal to 5. So it is a fifth order filter. In the similar way, we go to table 8.6, I believe, and then we find out 0.5 dB ripple. At 0.5 dB ripple, we find out what is n equal to 5. And then when we find n equal to 5, then we get these values. Of course, you already know that this value, no need, because this is 50 ohm. So we have these values here. So with these values, again, we will approximate first the prototype low pass filter, and then from low pass filter we'll convert it to a band pass filter.